I'm Chris Schroeder.
I'm Brent LeDuc.
And I'm Mayor Carey.
For this video project, we decided to do a study in projectile motion.
What we decided to do was take 3 golf balls and hit them at different launch angles to see how their initial velocities and distances and time, how long it took them to cross those distances would compare to each other. For our first trial, we approximated a launch angle of 25 degrees. For our first trial, we decided to hit a lower arcing golf shot and try to determine what the initial velocity was. We did this through measuring the distance that the ball covered, how much time it took to do that, and through interpreting the videos we were able to figure out approximately what the launch angle was. So the distance D was equal to 54.5 feet. The time it covered it in was 1.31 seconds, and our theta was equal to 25 degrees. We decided we were able to use a constant acceleration equation because gravity was all we had for the projectile motion. So what we started off with was finding the initial velocity in the x direction using this equation. The initial x position goes to 0, and all of this goes to 0 because there is no acceleration in the initial x direction. So we start out with 54.5 feet. The 54.5 feet is equal to the initial x velocity times the 1.31 seconds. So in order to find the initial x velocity, we take the 54.5 feet, divide that by 1.31 seconds, and that gives us an x velocity of 41.6 feet per second. Now in order to calculate the actual velocity, we'll have to, in order to take the x component, convert it by the angle in order to find the actual. So we know that the x component velocity is equal to the actual initial velocity times the cosine of the launch angle, which is 25 degrees. So in order to find the initial velocity, we take the x velocity, which was our 41.6 feet per second, and divide that by the cosine of 25 degrees. And after all that, you find out that this comes out to approximately 45.90 feet per second for our first shot.
For trial 2, we had a launch angle of 35 degrees, as you can see in the picture. For the second trial, we used the exact same equations. The only difference was the initial launch angle, where the moment of impact where the golf club hit the golf ball, it was an angle of 35 degrees. The final distance we received was 46.542 feet, and our time was 1.57 seconds. Now in the first equation, we used our constant acceleration equation to find our launch angle in the x direction, which is x final equals x naught plus v t 1/2 a t squared. That goes away. And now we just plug in the numbers. 46.542 feet equals the initial start of the distance is 0 plus v naught in the x direction times 1.57 seconds. Therefore, v naught in the x direction is going to be about 29.6 feet per second. Now finally, we can find the actual initial velocity for the golf ball. Using V naught cosine 35 degrees equals 29.645 feet per second, and our answer comes out to be 30.85 feet per second.
As in the previous two trials, we analyzed the launch angle to be 55 degrees. For our third and final trial, we had a distance of 13.79 feet. We had a time of 1.15 seconds and a launch angle of 55 degrees. This is a much steeper launch angle than our previous two trials, so it does have some impact on distance and time, as you can see here. So as with the other examples, we are going to use the same constant acceleration equation of x equal x naught plus v naught sub x times time plus 1/2 at squared. As before, this term will go to 0, and so will our x naught term. And then we will write down what's left. So delta x is equal to v naught x times time. And then at this point, we can rearrange one final time to have v naught x equals delta x over time. And at this point, we're now ready to plug in our values. So our delta x value is 13.79 feet. And our time is 1.15 seconds. When you punch this into your calculator, you should get 11.99 feet per second. At this point, we can now take and find the initial velocity using the launch angle. So we'll go and we'll have a different constant velocity, constant acceleration, equation. And we will have v naught x is equal to v naught times the cosine of our launch angle theta. So we'll rearrange that. V naught is equal to v naught sub x over the cosine of the launch angle theta. And once we plug in values here, we'll have 11.99 feet per second, will be calculated above, and we'll have cosine of 55 degrees. And if you punch this into your calculator, we got a value of 20.91 feet per second.
Just to give you all a little bit of insight, my intuition, being a golfer, understanding, kind of predicting what was going to happen with all these shots. The first shot, is described as a punch shot. It's a real low arcing, fast shot, which is why it had a higher initial velocity, because the idea is to cover more ground to try and get it to roll further down so you can actually get out of, low-lying stuff that's designed for like tree shots. The second shot was just pretty much a standard shot. So having it go less distance than the first, higher angle, and probably higher time, was kind of what I intuitively thought. The third shot's a flop shot. It's designed for a really high arc and very low speeds because you want it to pretty much stop wherever it lands. So again, intuitively, that third shot, much higher launch angle, a much lower speed than all the rest of the shots. So intuitively, it kind of followed everything that I knew as a golfer going into this experiment.